Sorry. So I may go and just get us started and take my time on introductions and kicking it off while the rest of the folks show up. I know we already had a pretty large crowd joining us, so thank you. My name is Bart, Bohn. I'm here to help moderate our discussion today on how we're applying AI to help decarbonize our grid. We all know that our electricity sector is one of the bigger generators of carbon emissions. And so it's great to see some emerging brand new technologies come on the market to help reduce that climate impact. So a little bit my background. I work with the University of Texas, where I run its Startup Accelerator program. Also run a startup incubator program based on cybersecurity, which gets into lots of fun nooks and crannies of the world. More relevant to this conversation, previously I co-founded two what would now be called AI startups. Back then they were just called big data machine learning startups. The first was focused on graph data, so try to understand the relationship and the value of the relationship between data sets. And the second one, we explore the value of time and how that could be applied to the retail sector. So again, it turns out time is becoming a much more critical conversation as we think about the grid as well, given that the balance that it has to always be in. In the last part, I just want to set up the conversation. AI is kind of this big mystical thing right now. It's kind of the big sexy, it's way overused. The reality is all kind of mostly boils down to statistics at the end of the day. And just kind of how do you use those statistics? And so this conversation won't be about how 9,000 necessarily, much more realistic ways that we're able to impact the utility grid today in the coming near term. So for what we're going to do is have three speakers. Each one's going to speak for about 8 or 10 minutes. Please submit questions through the chat. And if there are some very direct, succinct, clarifying questions, we'll use those. We'll bring those up after each speaker just to make sure we get everyone on the same page. And then towards the end, we'll have a much more, we'll of course keep track of all the questions and have a much broader conversation, just deeper discussion afterwards with those types of questions. So with that, we'll do each speaker to introduce themselves as they kick off their portion. And we're first going to start with Kimberly. So Kimberly, I'll turn it over to you.
Great, thank you. So I'm Kimberly Gilbert, and I work for Beyond Limits AI. And Beyond Limits has licensed technology that comes out of NASA and JPL. The technology was initially created to go into space where there isn't a lot of data. As Bart said, a lot of it is big data, it's numerics, it's statistical analysis, but we don't know much about deep space. So NASA and JPL worked on combining all of the numerics, all of the data with symbolic AI so that the Mars rover could land properly, so it could stay alive while it was on Mars and learn while it was there. So we have taken that technology and begun to implement it to make companies perform better. And so one of the things that we've been working on is how can we make power generation stations run more efficiently. So if you go to the next slide. In the summer, I attended a webinar that Utility Dive put on, and they had surveyed different utilities on how their organizations were likely to change over the next 10 years in terms of the mix of power resources. And by and large, everyone said solar, increasing wind, increasing battery storage when it's available and viable. And then primarily on the other side, decreasing and decommissioning coal and nuclear power plants. So natural gas is somewhere in the middle because it's so much more efficient than coal and oil. And it's also needed to help in the transition. So our focus has primarily been on natural gas power plant. How can we help natural gas power plants run more efficiently? Okay, so next slide, please. I don't know if I have control. Okay, thank you. Okay, so when we're thinking about decarbonizing the grid, as I said, we're thinking about decommissioning coal, nuclear, some natural gas, and we're recognizing that it's going to be a very long transition period. So it can take us to maybe 2045, 2050 before it's complete, the transition to renewable. In the meantime, there's going to be a lot of adjusting to the inputs of the solar, inputs of wind. If the wind stops blowing, how do we compensate for that? And so repurposing, in this transition, we can use natural gas, repurpose natural gas, and because they have the ability to turn down capacity, ramp up and down more quickly. So I guess the upshot is, over the long transition period, we need to provide reliable, inexpensive, and ubiquitous power and stable power while undergoing this transition to renewables. But we all know that power plants, and as in most process industries, run really well when they have a really good operator running them, right? An operator, a dispatcher, an engineer. When you have people who understand the systems and have years and years of experience, things go better, things operate more efficiently. And when a power plant runs more efficiently, it produces less CO2 per unit of energy that it produces. So we would argue that, next slide please, that it's not just the data that matters, it's what the workforce knows. So to make the power generation station run more efficiently, we have to encapsulate or encode what the operator knows before they retire and take all of those years of experience with them. All right, so next slide. So what we do at Beyond Limits is that we take that subject matter expertise from the operator, from the engineer, from the dispatcher, and we encode it and create a knowledge base. And that knowledge base, it really can be seen as little tidbits of information to provide context, rules. It can be information on constraints. It can describe trade-offs between, when you should push something a little harder. If you push something a little harder, like a turbine, what does that do to the maintenance? What does that do to safety? What does that do to the economics of the situation? And we combine those tidbits of information with the power plant data. So then we're still doing machine learning to identify trends and patterns, but then we're weaving into that knowledge. And what that allows us to do is, when something goes wrong or when something isn't operating at maximum efficiency, we can, one, flag it, identify it and flag it, and then we can make a specific, or the AI rather, can make a specific recommendation about what to do about it, and then also explain why that specific recommendation has been done. So what this will allow the plants to do is it will allow the inexperienced operator who's coming in to replace the very experienced operator to run the plant at the same level of efficiency as his predecessor did, because it has the recommendations of the AI. Next slide, please. So what this means is, essentially, we're working toward a more cognitive power plant that can maximize the uptime of the plant and reduce the carbon output by running more efficiently. So the AI provides rapid, near real-time actionable intelligence, so it tells the operators what to do, giving them the next best action to recognize, mitigate, and prevent problems. With the idea that primarily we're trying to help them efficiently cycle the turbines to follow the load, especially in response to wind and solar, which are notoriously spiky, to maximize the uptime, to extend the asset life, and to prevent unexpected system trips. So just to look at that a little more closely, one more slide. I wanted to talk just more specifically about what that might look like. So for uptime optimization, for following the load, if we encode the tidbits of knowledge, how the operator recommends doing startups and shutdowns, when do they bring assets online, in what order do they bring them online? Is it better to pull back a turbine or turn it off altogether. So, so making recommendations about startup and shutdown regimes, making recommendations about how to follow the load in the most effective way, but staying within the constraints, and then how to do that in the most efficient way so that you're not damaging the equipment, you're maximizing the economics, and you're maintaining safety. So that's one sort of use case. The other use case, which is tied in, is how do we help keep the assets healthy and running them most efficiently? So through machine learning, we can identify anomalies. And then through the symbolic, weaving in the symbolic information, we can identify what happened, make a recommendation about what to do about it, and then explain why we're making that recommendation. So that's the step that's a differentiator. The same would go for alarm mitigation. If there's an alarm going off, often that causes other alarms to go off and can lead to alarm flooding. The operator doesn't know what to do. So the system can identify which alarm should be paid attention to and what should be done about it. And then finally, as often happens in these plants, the equipment slowly is trending toward failure. So something is going off, maybe a bearing is a little bit out, or something is trending toward failure, and it's difficult for an operator to see because the trend is very slow. So the system can, by incorporating the numeric and the symbolic AI, can identify when that pattern is happening, and then again, based on inputs that we've gotten from the experts, can make recommendations about the next course of action. Okay, that's all I had.
Very good. Pause to see if any questions come through. I know for mine, just the obvious question of how are you getting the expert advice? Are you doing interviews, or are you passively collecting that data set in some other way?
We have the capacity to do either. I mean, typically we get manuals. So we're working very strongly in refineries, and we're moving into the power industry. But we use manuals. We have direct contact with the experts. Usually there are multiple experts, so there might be an engineer and an operator and a dispatcher that we work with simultaneously. So it can be via one-on-one communication or through emails, any sort of documentation we can use as well.
Okay. And for the more experiential wisdom nuggets, are you able to look back in operating data to validate or quantify what they're describing?
What we're doing currently in refineries is we are providing a retrospective view. So you can look at historically over the last month or over the last months when something was running out of spec or not according to the plan, not at the most efficient, when there was a mitigation step that was available, and when the mitigation was taken versus not taken. So if the mitigation is not taken, why aren't they taking the mitigation step? Is it because they don't trust the system? Is it because they're taking a nap? Is it, so there is a retrospective view at this point. We haven't fully, our intent is not to automate the system because we just don't feel like the AI is there yet. So we always want a human in the loop. We want a human to ultimately take the action, but we provide all of the information to help them take the action with the most information available.
Right. And that comes up right on one of the questions that came through. Operators kind of know by sound and feel, just kind of feeling something vibrate, you can pick up some of that. This could be able to look at action taken or not taken against those. Okay. Very good.
Yeah, that's right. They get to make the ultimate choice.
Okay. Very good. All right. So with that, we'll pause on kind of the clarifying questions for Kimberly. Switch over to Stas. So please, if you have more deeper discussion questions from her topic, please load up some of those types of questions. We'll get to them after all the speakers. With that, Stas, I'll turn it over to you.
Sure. Hey, folks, I'm Stas Gayshan from the Cambridge Innovation Center. So just a brief word about CAC. CAC, the Cambridge Innovation Center, has been around. We're now in our 21st year of operation, which is a pretty crazy thing to say. CAC builds shared space communities for startups. We started, as you might guess from our name, in Cambridge, right across the street from MIT in the late 90s. We built a community for some of the most interesting startups addressing just a multitude of global challenges. And about 5% of our startups are working in energy, and another 4%, give or take, are working in data science, machine learning, artificial intelligence. That's a percent out of about 2,300 now companies across the CAC locations in Cambridge and Boston and St. Louis and Miami and Philadelphia and Providence, in the Netherlands, in Rotterdam, and we've got new centers coming online this year, hopefully, in Tokyo and Warsaw. CAC provides physical space and a set of resources to these startups and friends of the startup community that can help them grow and scale their innovations. So those 2,000 plus companies represent a little bit more than 6,000 people who go to work in those companies building the future of everything. And I thought this was a very interesting topic because there are actually many startups and companies at CIC that are looking at how to decarbonize the economy broadly and generally. And then some are doing very interesting specific things. So I'll talk a little bit about some of their efforts, but I thought that in general, if you kind of look at approaches for decarbonizing the economy, there are a couple of different thematic categories that you could probably take a look at. One is decarbonizing power generation and making the generation of power more productive, more efficient. Then there's also transportation of power, which I think you can kind of put together with generation into kind of the larger category of the power generation cycle, generation and transmission. Beyond that, of course, there's also questions around how to use power. How much do you need to get? And there's one of the decarbonizing questions is you can decarbonize the production, but you can also decarbonize the consumption. And if you can have lower consumption of carbon-based fuels, that can be sometimes a better effect than switching power plants to more clean sources, because at the moment, even building zero carbon plants requires quite a bit of carbon pollution in terms of materials and others. So across that, we have a number of companies working on a series of problems. So I figured what I would do is I would just take a look at my other screen. I'm going to tell you about a couple of different stories that are happening in our world of folks who are working on really, really interesting and fascinating stuff. And I kind of close with some general thoughts. At CIC, in addition to the startups themselves, we actually have a number of venture capital firms. So just in Boston, Cambridge alone, there are now 23 venture capital funds that base themselves at CIC. And there's more venture capital at CIC in Cambridge and Boston than there is in the UK as a country. And enough there that if CIC was a US state, it would be the fourth largest state in venture capital if you just take the money headquartered at CIC. One of those funds is a company called Procyon Ventures, and they actually invest in a lot of AI and machine learning. One of their investments is a really fascinating company that's working with the city of Walnut Creek and looking at how do you drive transportation more intelligently. This is on the consumption side of power, is how can you have people spend less time circling around in parking lots? Because if people spend a lot of time circling around, they're consuming an enormous amount of energy. So they're working to allocate the transportation efficiency of folks by pushing people from the outlying suburbs of Walnut Creek who are coming into the city, and in convincing them through a number of programs looking at how parking works, structuring the incentive programs to build a path so that people who are coming in from outside the city on a regular basis can actually park in the periphery and take public transit inwards, so that they're lowering the amount of pollution that these folks create every single day by coming in and taking up parking spots. And then opening up parking in the center of the city. Walnut Creek is still a pretty car-centric place for folks who are coming in for retail and shopping purposes, so that more space is left for them, so that these folks are not circling around the pizza shop, circling for parking for 10 minutes and then leaving and spending 20 minutes of that just driving around looking for that parking space to run in for 30 seconds to get a pizza. And so it's a very, very interesting concept. They spent a lot of time figuring out, Kimberly, to think your question, and something that you're dealing with, how do you actually think about what the data is that's relevant? Because it's not sort of all data. You have to take data and then use the people who exist in your ecosystem to look at that and say, okay, now that we know this, now that we've run some analysis, what's a conclusion that makes sense, and how can we integrate the insights the AI and the machine learning is giving us with the insights that humans have? Like, not every car coming to the city is actually doing the same thing. So that's kind of one very, very interesting resource. There is another company called Blue Sky, and they're looking at AI for aviation. So as we know, aviation is a huge contributor to the carbonized economy. And getting airplanes to waste less fuel and run more optimal routes will have a huge impact on the amount of carbon pollution they generate. And for now, we don't really have a way to travel by air carbon free. So the first thing we have to do is reduce the amount of energy used by the air transit sector. So Blue Sky is actually looking at this. The folks who started the company spent a lot of time in looking at systems engineering, and they're working with airlines to help them meet the UN Sustainable Development Goals in thinking about how do you build a carbon-free economy. So I think that's really fascinating. We have another company called Voda, which is, I think actually they're trying to say Vada, which is the Russian word for water. Voda has a machine learning engine for water. So they're looking at again, another one step down, which is we spend a lot of energy when we're creating water systems for our communities. We spend a lot of energy getting water from a place, transporting water to another place, cleaning it, filtering it. And right now, a lot of our pipes, especially our water pipes, leak. And historically, this hasn't been a huge concern, because if clean water leaks into the environment, that's a financial cost, but it's not, let's say, as harmful as oil or gas leaking in the environment. So people haven't spent as much money maintaining clean water pipes. And the outcome of that is we laid them, in some cases, over 100 years ago, and they're leaking, and they leak a significant amount, which means we're generating energy upstream, cleaning water, cycling water, moving water, and then losing water on the way to its ultimate end users, the consumers. So Voda actually uses machine learning and AI to look at data sets with third-party data and utility data on things like satellite images, and looking at satellite images of soil and land use to figure out when the pipes will break. Kimberly, this is kind of reminding me of what you were saying on what kind of maintenance is deferred when and why. And this is a combination of a machine question and a human question. And so Voda kind of works on that. And then kind of continuing in that world, Spacemaker is a company that uses artificial intelligence to think about how do you design better cities. So they have automatic software that can run to help architects design smarter building shapes that can use less land and more space, so that the carbon used in the transit of materials and the use of materials on site can be further reduced. And they're actually thinking a lot about building smart cities that can be more energy efficient, not only in their day-to-day operation, but in the most energy intensive and most carbon intensive step, which is their construction. And so it's kind of another way of using machine learning to think about one step down in the cycle, which is how do we get less energy used on the production of materials and the transport of materials and the use of materials, so that we're creating less waste in the construction of our cities. And finally, I just want to mention See Ahead. So See Ahead is actually not a machine learning company. It's in fact a community for deep ocean startups. And the deep ocean is a place where we both generate energy in wind and water, wind and hydro and solar with wind and waves and sun. But it's also a place where we transit energy across oceans. So there are a number of folks who are in See Ahead who are convening companies to look at hybrid propulsion and optimized transit routing using, again, weather patterns and plugging in weather data and movement data into AI and ML algorithms so that ships transiting oceans can do so more efficiently and more effectively. And then that can help reduce the amount of energy used by our large-scale grids and can reduce the amount of transport of fuels that we need across oceans if we can use the materials effectively in the place where they land, and we can send them more effectively in our transportation methods. We can end up with a more efficient, less carbonized grid. So hopefully that's a bit of an overview of some of the efforts that are happening at various companies at CIC and companies that are part of the ecosystem. For me, the really fascinating thing in spending time looking at these companies and engaging with them is figuring out how they can better connect to the world so that they are able to get their tools into the hands of more consumers, and in their cases, many B2B consumers. And for CIC and the 2,000 plus companies that call CIC home, it's pretty exciting to be part of building a better future. So very excited to be here. Thanks for having me here, and happy to talk more about what's happening in our world of startups and ecosystem creation.
Great, Stas, thank you for that. I'm just gonna a couple questions follow up to see if other ones come through.
Sure.
On the water side, I like the emphasis. I know in Austin, I think something like 12% of our power is consumed by our water utility, and it's one of the challenges is the most carbon intensive water is the stuff that goes down your drain. And so the farther into the system it goes before it's lost, the worse it is. So I like that they're really trying to think about how to capture and prevent that kind of carbon impact. I think a question that could actually be for Kimberly, you as well as Stas, particularly on the aviation one. Auditability of the model. A lot of times ML models end up black boxes, and it's kind of hard to know what happens inside of it and how it's making decisions, particularly as so many of these use cases intersect with regulatory conversations, or at least public good. Is there a quick comment for either of you on that one?
Machine learning is typically black box because it's understanding the statistical relationships essentially between the different parameters. But the way that we approach it at Beyond Limits is that we break the machine learning up into smaller bits, and then we weave in the symbolic. And so we can interpret each output from machine learning and then combine those in a way that's meaningful. So let me give you a very quick example that's simple to understand. So you can use a neural network to identify a desk by showing the neural network 1,000 pictures of a desk, and that's training it to identify a desk. And you will never know why it identifies one thing as a desk and another thing as a coffee table, right? But another way to get the AI to identify the desk is to show it 1,000 pictures of a pencil and 1,000 pictures of a laptop and 1,000 pictures of a table and 1,000 pictures of a chair. And then to use the symbolic AI to say, if there is a table and on that table there is a laptop, there's a 50% chance that that's a desk. If there's also a pencil and paper on the desk, then there is an 80% chance or a 90% chance that that's a desk. And so if it then identifies this as a desk, then the rationale or the explanation would be, we've identified that this is a desk because it contains a pencil, paper, and a laptop, and it's a flat surface. So, so we are not providing insight into how the neural network identified the pencil as a pencil. that we still can't do. But by breaking the machine learning up into smaller pieces, we can help interpret how the different pieces are fitting together. Does that make sense?
Yep, that's
Sure.
good. It's way, I like how it builds upon itself, and it's explainable. More importantly, Stas, I saw you lean in.
Sure. Yeah. And Kimberly, that's actually fascinating. It's fun to hear this stuff. I think for it's harder for me to speak to the details of the companies, but I'll tell you that the founder of Blue Sky actually came out of work for ICAO, that's the International Civil Aviation Organization, and he ran the working group on CORSIA, which is the Carbon Offsetting and Reduction Scheme for International Aviation.
Right.
And so I'm pretty sure that at least some of that work is public within CORSIA. I was just checking out their site to see how much of CORSIA's work is public, and it seems like quite a bit of it is. So I don't know whether his models are public, but I know at least some of the end results and some of that data is public. So if you want to take a look at it, you can look for Blue Sky, but you can also look for CORSIA, which is the Carbon Offsetting and Reduction Scheme for International Aviation. And that's a mouthful, but figure that that's a good place to look at where those models are if you're interested in learning a little bit more about them.
That's a great background for him to come out of. That's an important organization that's starting to get more and more traction in the last little bit. So with that, we'll pause there and we'll shift over to Suzanne.
Thanks, Bart. I appreciate it. This has been a really great conversation to hear so far. Clayton, I think actually, can you run the slides for me? Because I'm having a little bit of problem when I take over. My mouse stops working for some reason. So while that's getting queued up, I'll just do a quick introduction of Pecan Street. We are a research and development organization based here in Austin, Texas, that focuses on accelerating solutions for climate and conservation in the residential sector. We do this through, you can go ahead with the next slide, please. We do this through a very data intensive model, and it's perhaps what we're most well known for if you've heard of us. We've created and managed the world's largest database on residential energy and water use. In addition to creating data, we carry out a lot of research as well at our lab that we have in Austin and in a variety of research networks that we've established around the country, with the center of that being in Austin as well, with the neighborhood called the Mueller neighborhood. And next slide, please. Through those research networks, we sign up households to volunteer with us, and then we install a variety of sensors in those homes that collect really high granularity data on how they're using energy and in some instances, water and natural gas. And essentially we turn families like these into, next slide, please, this kind of data set. So these are direct measurements. These are not estimates based on disaggregation algorithms. And it just gives you an idea of the kind of data and the size and scale of the data that we're collecting here at Pecan Street. We've been collecting this data from about 1,000 homes for the past 8 years. And over the past 2 years, we've upgraded a lot of those households to go from 1 minute data collection to 1 second interval collection. And next slide, please. We're able to make all of this data available through an online data portal called Dataport. And we've had a few thousand researchers from around the world, as well as a number of large companies and startups, license out the data to use in developing solutions, again, that tackle climate and conservation, but from a market consumer technology perspective. And that's part of our theory of change at Pecan Street, is that policy and regulations are really important to guide markets, but technology tends to evolve faster than policy. And so helping apply all of the investments that are happening in consumer tech and data creation, data management, AI, ML for better consumer insights, and use that to create solutions that people are interested in buying, that work really well when they're assembled together, like solar and electric vehicles, put better value propositions around those technologies and figure out how to optimize them so we have a broader and better social impact. Is the focus of our work. Next slide, please. So we've gotten drawn into this AI conversation quite a bit over the past few years because we're known kind of for being the data group in the electric grid decarbonization space. Through the course of a number of our research projects that are funded by the Department of Energy, we've identified a handful of optimization opportunities to let distributed energy resources provide more value to the grid, solve more problems, to modernize the grid, to make our power system more reliable, and to do that with these clean energy resources that households are buying, and to be able to quantify that value to the utilities so that we can then return part of that to the households so that we can accelerate that cycle of adoption. And at the same time, putting into place these solutions that let the grid expand their hosting capacity for distributed energy resources. Next slide, please. So these are some of the value propositions that we've identified, and particularly these come into play as we see the rise of smart inverters coming onto the grid, paired with rooftop solar, as well as energy storage and electric vehicles. And the reason AI is critical here in unlocking this value proposition is that all of these things that we've listed here, voltage regulation, frequency stabilization, those really rely on that distributed energy resource. And I'm just going to go with solar now to ease the vernacular here. To let solar respond in real time is the key. So where we have solar tied to smart inverters, it's already observing a variety of information about the grid, and it has the capability to respond to those needs. What we need to do is create algorithms that can then be applied to those resources that lets them provide that response in a way that, when aggregated at different scales, provides benefit to the grid instead of potentially introducing risk. So there's a lot of things that go into that, and I can dive into more detail on any of them if there are questions around it, but things like cybersecurity, consumer protection, the data exchange that needs to happen between these customer-sided resources and the grid to allow for that real-time response. But really, without AI applied to those smart inverters and to those smart DERs, we're not going to be able to realize this value proposition, and we're leaving a huge part of the potential value and the climate benefit and the economic benefit of rooftop solar, of residential energy storage on the table. And that seems pretty absurd in our current climate crisis. So we're really trying to push the conversation here, push the envelope around getting more of the kind of data that we know needs to be created to get robust, auditable, verifiable AI algorithms developed. We can test all of these in our research networks at Pecan Street. We've got a smart meter research network that we manage. We have all of these homes that you see in this beautiful picture here, part of our research network. We also have similar research networks in New York and California that have very high levels of adoption of EV and solar so that we can carry out this kind of research. Next slide, please. And one of the ways that we found useful to talk about this, to talk about what that kind of AI solution actually means and how it would operate, how do you break down decision-making between grid edge resources. Really, we're talking about building level resources, letting them respond in real time, uncontrolled except for the bounds of the AI algorithms that would be applied, and also have central control, and then sort of a third party that is becoming more popular, an aggregator, participate. We get a lot of questions from utilities around how is that even possible? Like, that's so far out of the bounds of how we can think about managing our grid right now, that it seems not like a short-term solution. So something that we found useful to bring into the conversation is this metaphor of an octopus, which scientists have only in the past couple of years really begun to understand how octopuses operate. Next slide, please. So I have a little video here that I'm going to make you watch about them for a second. I'm going to wait for it to tee up, but in the meantime, I'll say that octopuses, as you probably all know, because everybody's seen them move, have been a mystery to scientists because it's been unclear how each of their arms seems to operate independently from the other arms, but yet they obviously are a coherent, very successful organism. They move incredibly quickly. They have a variety of adaptive responses. They can change their color and the texture of their skin very rapidly. And these are the kinds of things that we're talking about with an AI solution for grid edge resources, that rapid response capability where you have everything working together towards a common goal as one system, but the ability for independent resources to make their own decisions. And so that's what we see here. This is actually a group of Israeli researchers who were able to use data and machine learning to figure out exactly how an octopus moves. The green line is the direction of its head, and the blue line is measuring and tracking the direction of one of the arms there. And you can see that they don't move in the same way. And that's because octopuses actually have embodied intelligence. So they have a peripheral nervous system that's sensing information and responding in real time, while their brain controls a specific set of instructions around response to perceived threats and overall trajectory. Individual arms can make decisions about how they want to manage that information that they're getting from central control. You can move on. I don't think we need to make people watch that again. And so that's the same kind of grid system that we're talking about here, and that we actually have all the capabilities right now to develop from a data and from a technology perspective, but it's just getting enough data together on both the grid operation, actually grid and feeder grid system design, which is really hard to get, and understandably that information is classified for cybersecurity reasons, but figuring out how we unlock access to more of these types of data about the grid, about DERs installed on different buildings in a way that protects our security collectively and individually, that ensures there's going to be broad social value from sharing data about our social systems is important, and that's really the missing piece to letting this AI solution that we think has really high potential, both from a climate and an economic perspective, to provide benefits. So this is more of a technical description of how we think the grid should be modeled after octopuses, where you see, again, the integration of central control for specific sets of decisions, aggregators for specific sets of decisions and responses, and then the ability for those individual assets to respond in an automated way. And some of the questions that I'm hoping the audience will decide to bring up, or that we can touch on in a future discussion, are how utilities can begin to think about a framework to participate in developing these types of AI solutions, to procure them, to work with companies, what data and systems should they be working on making access to, or even just collecting to enable these solutions to be developed, because as all the panelists have talked about, very specific data sets are the key to creating an effective AI solution. And I think something that's also been exemplified in this talk is that AI is use case specific. From a utility perspective, a lot of the questions that I get when we're talking with our partners or we're at utility conferences, imagine a deep neural network for AI that can cross the grid, like a software solution that's going to all of a sudden integrate a bunch of different resources and manage them automatically and in an automated, intelligent way. And that's probably not a near future reality for us, but there are a lot of really specific use cases where we do have data, we do have an economic opportunity that's going to draw in entrepreneurs and innovators. But we need to figure out how do we make that data more broadly available, and also how can utilities and regulators direct these entrepreneurs and innovators to creating solutions that we know are needed to modernize our grid and to achieve state or national level clean energy objectives. And again, at Pecan Street, we think distributed energy resources are a critical part of that solution. And we hope to see more of these types of conversations taking place in the near term. You can go to the next slide, please. And I'm happy to share these slides with anybody that's interested. This is more of an kind of engineering-based diagram about how we see this decision-making process breaking down, again, when we start to enable AI to be applied at the grid edge. Next slide, please. And I'm going to pause here, but we do have some additional information we can share if the audience is interested around the data access and enabling that real-time response between customer side of the meter resources, customer-owned data and assets, and centralized grid management. And Bart, I'll let you take it from here.
Great, Suzanne, that was really good. We got a couple clarifying questions just on what you were bringing up. The first is, was the hardware being installed in people's home to generate that data set?
But so there's two questions perhaps there, so I'll answer both of them. So from Pecan Street's data that we collect, the graph that I showed about household energy use, and we collect the same level of data on energy generation when there's solar present in the home. That's a device that's commercially available. It's what we've been using for almost a decade. So we are happy customers, happy to recommend that to anybody. It's called an eGauge device, and it's CT collars that wrap around the circuits in homes and take those measurements. Smart inverters are what enable the kind of AI-based solution that I was describing, where they are observing information about voltage, frequency, current on the grid, and then they have the communications capability to ramp up and down solar production, and also to provide data on solar generation back to an aggregator or to the grid, so that you get validation or verification of how that solar system's responded to calls for curtailment or ramping.
And on that type of response, there was a question around, has AI been really incorporated into any power electronics, presumably on the residential side of the meter yet, in order to have a more sophisticated response, perhaps either direction?
Yeah, that's a good question. Which I think kind of gets back to, what do we consider to be AI?
Yeah.
So there's a lot of sophisticated computing that's happening now with customer side distributed energy resources, like with energy storage systems, for example. You have a lot of safety protocols that are built into those batteries, where they're observing information about their surroundings and about the battery itself, and making very rapid decisions about the operation of that battery to ensure that it stays within established safety parameters for things like temperature of the battery. That's sort of an AI solution. But if you're talking about kind of a coordinated response between different devices or different assets, where you're observing information, making an autonomous decision based on intelligent information and intelligent guidance, we haven't seen that really get integrated at scale yet, but our team did create a system that does that, where we developed a hardware software device that observed solar generation from households, and a paired device on electric vehicle charging systems. So it was able to observe when there was excess rooftop solar generation on neighboring homes that shared a transformer, and then ramp up and down EV charging to absorb that excess PV, so that a house without solar, say, or without sufficient solar to charge the car, was still getting that car charged with sunshine, and at the same time preventing backflow of power onto the grid, which decreases the grid's hosting capacity for DERs if that happens at a high enough level frequently enough. So that technology is totally out there. We just assembled that with kind of off-the-shelf components, and our CTO did some software to develop that code.
Okay, I think those are the core clarification questions. There are some broader ones, Clayton, if you want to switch over back to the main slide. There's one that I think I want to ask the question of you, Kimberly. I use the word audit instead of explainability. That's perhaps something that we should dive into just a little bit, because that comes up a lot when you start thinking about how AI or machine learning in general could impact our public environment. And what, to me, you described you used an explainability example more so than an audit example. Is there anything more you want to perhaps describe on that to clarify or bring that discussion up for everyone?
In the context, again, I'll give a refinery example, and the reason I'm doing that is we have deployed refinery software, which is doing similar things to what we are currently working on for power generation. So let me give you an example in that case. In refineries, they have plans to operate the most efficiently or the most economically. And when they're not operating to plan, something's out of specification, and refineries are notoriously complicated. So the system will identify something that's out of spec or not operating according to plan, and make a recommendation. And because the recommendation is made to an operator that perhaps can feel the vibrations or know what's going on, the operator wants a good explanation of why. So the operator can look at all of the different considerations made by the software, made by the AI, and why various considerations or potential mitigations were rejected. So the operator can look back and see that maybe the reflex ratio would have been an option, but that couldn't be changed because that would put too much pressure on the column. And so, another option was changed or was recommended instead. So I'm not sure if that's the level that you're getting at, but within Beyond Limits, that's what we would call an audit trail. There are other things, depending on the specific use case, we use slightly different terminology. So if you have more clarifying questions, I'd be happy to continue to answer that.
Yeah, just a question that was brought up on audit, and those two are very fine lines. If you can track the actions taken and perhaps even the math behind why that was taken, so you understand the error or risk rate of that, then you have a really good audit trail that perhaps you can make sure that it's within the bounds that was deemed acceptable for that operations. So sometimes those are tough things to work out. Another one came back, just a very broad conversation around how for the various scenarios you're describing, are you calculating environmental benefit?
So we don't, at this point for power, we don't have quantified benefit. We are currently working with BP and an external auditor to calculate the carbon reduction or the carbon impact of making the refineries run more efficiently. So we're currently working on that, but we currently don't have an answer.
Okay. Stas, do you have any comments on some of the examples?
Yeah, no, it's kind of hard to generalize across all of the different companies that are doing all sorts of different work. But I'll look into it a little bit more and get back to folks. If folks want to follow up with me, I can ask the different companies how they're looking at it, because I think there is, between marine and air and transit and water, there are a bunch of different things that are happening. So it's kind of hard to generalize and answer.
Yeah, it's great if you could just capture it and then like how much volume or metric tons, but in all the energy usage, it's a little bit more challenging. Suzanne, one of the questions that came up, where'd it go? Is there a local market for distributed energy resources? Is there pricing transparency that's starting to enable that yet, or are utilities still too far away?
Enable the kind of solution we talked about, or?
I think it's just a basic question.
So I think there's still more that hopefully we can do to get a better return on investment for DERs. They're still obviously really expensive and not affordable by most people. But by creating these types of systems that I was describing that provide more value proposition to utilities, and then running those through the kind of research network that Pecan Street has set up, where we can quantify at a high detail and validate that value to the utility, then we can start to unlock that return on investment in a better way. I think that's an answer to that question.
No, it seems like most utilities aren't there yet to actually have a active market for distributed energy, buying stuff from our solar, having a two-way system yet. Another question came up around just computing power. Mostly machine learning, you use a data set to train it, and that can take days or weeks to really train the model. But then deploying the model, the algorithm, usually you can do that with a much lighter computing load, and hopefully at the edge as well. Any thoughts from the panelists around that question? Is that a limiting factor to a lot of what you're trying to achieve today?
So, this is something that's kind of interesting. I was at CES in January, and all the talk at CES in January was actually about moving computing to the edge, specifically for AI and ML applications. And there were so many different companies that were building very specifically low power, high computing functions where they would be able to actually do a lot of the compute right at the edge. So instead of doing sort of pre-compute and then kind of very small analysis at the edge itself, there was a recognition that at least in many of the most obvious applications of AI machine learning, and the most needed ones and the ones where people were most willing to pay for were sensors that were then doing immediate interpretation of data in a remote environment where they're not connected to permanent grid power. So that's whether that's vehicles, boats, airplanes, drones. You know, drones are like a classic use case. You don't want your drone to fly into a tree or to fly into an airplane, and every ounce of battery that your drone carries up is less flight time that the drone can then fly. So you kind of have this thing where you want a sensor on every wing and every wingtip on the thing you also want to weigh a quarter of a pound. And by the way, you want it to fly for 30 minutes and see the world. And it's important for things like firefighting, because every minute that your drone is up, you know, remember the California wildfires, drones were really critical in helping spot people because they're much cheaper than helicopters. But every minute your drone can stay up longer. And also the further it can see with its sensors and the more it can understand from that data. Can you get all three and happen at the same time? Otherwise, you start to have real consequences for life. So I actually think this is not an either or question. I think this is a developmental question where there's a ton of very high-end custom computing that's being developed specifically to do computing at the edge, AI at the edge, that can do really, really sophisticated data work with very, very low power.
Very good.
And I'll just add on to that. I don't think computing power is the limiting issue here. It's important in that as Stas was describing, we've got more, better, higher processing power computing coming to all kinds of edges that are going to be unlocking more and more opportunities for AI. But you do need to have computing power to aggregate all of these different data sets that we're seeing now, that we're going to be seeing in the future, to then develop and run neural network-based AI on those data sets. But there's a lot of resources out there for that. And we're seeing just from use of our data, which is a petabyte of data, and the number of times individuals try to download that themselves and successfully are downloading the whole database more and more frequently, that's not really, that kind of computing power isn't a limiting factor for individual researchers either. And in large part to advances in computing and cost reductions there, but also because we're seeing more of a focus in advanced research on AI and ML development. And so there being resources put towards places like the Texas Advanced Computing Center to free up server space so that they can work with researchers on running these kinds of AI research questions. So there's a lot of interesting sub-themes there, but I wouldn't say that it's a limiting factor in any way.
Great. That actually brings us right to 1 o'clock very nicely. The last bit, just to remind everyone, this is recorded and links to the recording be pushed out in a follow-up email. So thank you everyone for coming. Thank you to our panelists, Suzanne, Stas, and Kimberly. Unfortunately, I had to drop off a moment ago. Thanks everyone for attending, and let's push the conversation forward to try to continue tackling climate change. Thank you.
Thank you, Bart. Thank you, Stas, for participating. And we have another webinar this Friday, if anybody's interested, where we've used some of our data to carry out real-time analyses of how COVID is impacting residential energy use. We've gotten a lot of questions around that, so our CTO, Scott's going to be available to talk about that at 1 p.m. Central Time on Friday. And it's free as well. Sign up if you'd like to join. Thanks, everyone.
Sounds great.
Bye.
Bye.